So, before starting today's class, I will show you. Yeah. So, some students posted the question about the lab assignment. Okay? So, actually, so in this lab assignment, we need to use the GTK wave. And then, the GTK wave uses the graphical graphical actually display engine. Well, it's also you need to code the display server in Ubuntu. But if you install the Ubuntu server version, then Ubuntu server does not include the display manager or the graphics server. So actually, in order to launch the GTK Wave, then you need to install the display server. Actually, it's called the X server because X display server actually. So and then this is the very actually you can just install the Windows manager. So I know this name is not familiar with you because everyone is very familiar with the GUI graphical user interface, such as the Windows or Mac OS. But the server operating systems, such as the Ubuntu server, does not include the this Windows manager or graphics environment. So actually you need to install the Windows manager, and then actually I posted this link, and then I recommend to you. I recommend you install the XFCE. Okay, so this is very lightweight Windows. Okay, and then actually also on Mac operating system, you can install Ventilator and you can install GTK Wave using Room. Okay. So that is the package management tool of Mac operating system. But problem is that also one student posted some information. There is that Sonoma new version. So actually, I do not use Mac operating system. So actually, I mainly use Windows or Ubuntu operating system. So actually, I don't know about some issues on Mac operating system or the newer version of the Mac OS. So actually, you can just see this information about the GTK Wave issues on Mac operating system. Okay. Any question about the lab? So, okay. And if you have any issues, then you can make an appointment with the TA, okay? And also you can visit you can stop by TA's office. Okay. Okay, so in the previous class, we learned about the basic knowledge regarding the design. So it is because in chapter 4, we need to learn how to design hardware architecture or processor architecture or RISC-V processor. So and then so this is the system. CPUs, GPUs, and most processors are part of a kind of digital system. So actually, in order to build or in order to implement the digital system, then we need to use the hardware description languages. It is different from the some high-level languages such as C. Actually, the syntax is very similar to C, but actually the purpose is different. So actually the purpose of HEL is to implement the hardware system, what is the system. So, but the purpose of high-level languages such as C is just implement software, right? Okay. So, and then actually, in order to build hardware systems, then we need to also consider some constraints and then real aspects of hardware. Okay. So that's why the proposal is different. And then I also unit. So this is very important concept. So you need to understand the clocking mechanism or clocking methodology. So actually in part one, chapter one, so we learned that the performance of a computer system is highly influenced by clock period. So it is because, as I mentioned, the CPUs use clock signals. Then actually, the most digital systems use clock signals to run or to run their actually to process the digital data or digital signals. So, and then we learned that the clock period, so that you can find the two state element. Actually, I mentioned that these are deep flip-flops, right? And then same clock signals are connected to the clock port of these deep flip-flops, right? And clock period. So and then also we can find the combinational logic between these two deep flip-flops, and then the clock period needs to be longer than the total delay. So this is the longest delay of this combinational logic. So which means that the delays of this combinational logic determines the clock period, right? And then why is it important? It is because clock period decides the execution time of a computer system, right? And then actually the execution time is proportional to the clock period. Okay, so so you need to remember this one. So this is very important. Okay, and this time, so we will start from some basic units in the very simple RISC-V processor. Okay, so we will start from Datapath. Then, what is a Datapath element? So, actually, so in the previous class we learned about we saw this here, and then it just assigns some components, other components of the RISC-V processor, like the program counter register, instruction memory, and register file, and data memory, something like that. And we connect these components with wires, so electric wires, and then through these wires, well, you can find the wires here. So through these wires, digital signals can pass from one element to other element, right? So you can find that data can delivered via these wires. Okay. Then what is a data element? So this is the definition of a data element. So data means elements that process data and addresses. So which means that if a certain component processes digital data, so the addresses are also kind of digital data. So if a certain component processes this is the data, and we can call this component is a data path element. Okay, so in a CPU, we can find several data path elements, such as the registers, ALU, and multiplexers, and memories like instruction memory and data memory. Why? So if you see these components, you can find that each component receives digital signals, right? So you can find the input ports here, and then through these input ports, these components receive digital data, right? And then this received digital data processed inside of this component, and output data are generated. So we call these elements, like these hardware elements, as data path element. Okay, so which means that the data can be processed inside of a data path element. So we can find several data path elements such as RISC-V, ALU, and multiplexers, and the memory, and the RISC-V, the CPU. And then we can start from the individual data path element, and then we learn how to build a RISC-V processor from individual data path elements. Okay. Also, in the previous class, we learned which steps are required for executing instructions, right? Do you remember? So, like this. So, instruction execution. So, in this slide, I explain. So, in order to execute instruction, these steps are required, right? And then in order to build hardware or hardware system for executing instruction, and we can also, so it's obviously we need to design hardware components that can perform these steps. Okay, so I will explain step by step for designing a data path element in this file. Okay, the first step is instruction fetch. So what is instruction fetch? What is fetch actually? So actually the fetch means that we can just do some branches, and then we can play with a dog. And so fetch means that it should just do some object to the other direction. So and then in the computer system, the fetch means that it just transfer. So it reads data from memory, right? So fetch means that actually you can understand that the fetch means it read data from memory. Then what is instruction fetch? Obviously, if a processor reads instructions from memory, and this process is called instruction fetch. Okay, you can understand that. Oh, instruction fetch is that the processor reads an instruction from instruction memory. So instructions are stored in instruction memory. And then we learned that we can read a target instructions using program counter, right? Because I explained that a program counter is an address of an instruction, right? So if the PC value is set, and then, so this is the program counter register, okay, so PC, and then the PC value is stored in this register, okay. Then you can find the output port here. So what is this value? This value is the current PC, okay. And then actually the clock is connected to this PC. So if the current PC is read from program counter, as you can see, this PC is delivered to the read address port of instruction memory. Okay, the address is given, and then if an address is given to a memory, then we can get the corresponding data indexed by its address. Okay, so which means that the memory has many data elements such as the mem, and then these many data elements. It is similar to an array, and then actually the data is indexed by address. So if this address is given to the instruction memory, then we can read instruction. So this is the instruction fetch. So PC is set. The PC is set for the current instruction, and then this PC value is given to instruction memory, and then a processor can read an instruction from memory. So this is the instruction fetch step. Okay. Understand? Then what is this path? So I just explained about this path, the PC to instruction memory. Then what is this path? So if we see this path, then we can find, this is the adder. Okay, so I said that this is the current PC. Okay, current PC value, and then you can find that what is the output of this adder. So what is the output of this adder? This is the current PC, current PC plus 4. Okay, because you can find the 4 here, and then I said that this is an adder. So the output of this adder is the current PC plus 4. And then as you can see, this value is for next instruction. So in chapter 2, we just learned about in chapter 2, we learned about the program counter. And then if the next instruction is executed, then we just increment the PC by 4, right? So this is this add by 4 is for this operation. Okay? So this is the PC will be updated for next instruction. Okay, and then in order to test the next instruction, we need to increment PC by 4. Okay, so as you can see, this PC value is connected to the input of program counter. So this is the current PC plus 4, and then actually this is the next PC. Okay, and then I mentioned that the clock is connected to this PC. Okay, so actually this program counter used this next PC value for the next clock cycle. Okay, so this is the instruction fetch. So we can design instruction backstep of a RISC-V processor like this. Okay, and then let's see the behavioral model. So, so this model just implement the system value code for the is design. Okay, so actually, this slide shows the part of code that implements program counter register. Okay, so as you can see, so this is the PC register, and then PC register is a 32-bit register. So because this is we are learning about the RV32I, right? So we are learning about the 32-bit computer system. So width of PC register is actually 32, and then we do not learn about the virtual memory yet, but actually the size, the width of the PC register is actually the same to the width of virtual address. We do not learn about the virtual memory yet. So, and then I said that this clock is connected to the clock port of the PC register, so which means that at the rising edge of the clock, the current PC value is updated with next PC value. Okay, so it's just a different from actually, and then also we can find the next PC value. Next PC is actually equivalent to the current PC plus 4. So this is the just behavioral model. It's a system value code. So you can find the PC underbar curve here. So it represents current PC, right? And then what is this one? So we learned that this code implements deep flip-flop using negative reset. Okay, so we can find the reset underbar B here. So if the reset is given, then current PC value becomes 0. Okay, this is the reset value. Otherwise, for the normal state, the normal case, PC current PC is updated with actually next PC underbar next, right? And then this value is the PC underbar curve plus 4. Okay, so this is the implementation of the program counter register. And then as I mentioned, the current PC is just updated at the rising edge of the clock using the next PC value. Okay. And then how about the instruction memory? So what is the memory? The memory is a data array. And then this data array is indexed by an address. And then, you know, this is an instruction memory. So address is actually current program counter, right? So, and then if the address is given, then we can get the corresponding data element indexed by this address. So you can find that this is the some data array, right? So this is the width of each data element. So we can find that the width is 32 bit, okay, because the single instruction size is 32 bit for the normal RISC-V instruction. And then you can find that this memory has 256 elements. Okay. Okay. Then what is the data out? The output. So I said that the output is indexed by the address. So it's data indexed by address, right? So what is the address? Address is the PC value. But the address is the byte address in RISC-V, right? But we can observe that the size of a single element for this instruction memory is it's 32-bit. So which is 4 byte, right? It's a 4 byte. It's a 4 byte. Okay. So which means in order to access the target data element, actually we need the input address. We need to divide the input address using 4. Do you understand? It is because the size of a single data element is 4 byte, and then address is the byte address in RISC-V. Actually, we do not use like this because we need to use the address and the 31 down to 2. It's equivalent to divided by 4, right? So this is the behavioral model of the instruction memory. Okay, then let's learn about the register read. So and then register read. So let's think about the R type instruction. So for example, add x1, x2, x3. So actually R type instructions require 3 register operands, right? And then actually okay. So R type instruction on R type instruction uses 3 register operands, right? And then RS1, RS2, and then RD. And then we know that this instruction requires read operands from registers, 2 read operands actually. So which means that we need to read 2 register data from register file, and we need to store 배터리 좀 나중에 끝나고. Okay, so for the R type instruction, then we need to read the 2 data from the register file, and then we need to write 1 data to register file. Okay, so and then I mentioned that a register file is similar to a memory, right? So you can understand like this. So this is the register element, and then register file includes an array of register data, and then each data is also indexed by register number, right? So we can understand the register like this. So which means that, so in this example, the for this add instruction, we need to read the X2 data, so data in X2 register. So this register number is 2, so which means that it's the register number 2, so indexed by the register number. So for this operation, the register requires the read register 1, so this is the RS1, okay, source register 1, and then read register 2 is the RS2. So which means that a register number is given to is read register 1 or read register 2, then the corresponding data is read out through is read data 1 port. So this is the 32-bit data. Also, so read data 2 is the read RS2. Okay. So we can read data from register file like this. So register number is given and the corresponding data is read out from the is read data 1 and read data 2 port. It's very similar to the memory, right? But instead of address, we use the register number. Then how about the write? So this is the RD, so this is the write register. So we can give RD, so destination register number to the write register port, right? And the write for the write operation, then we need to also give the data because the data is written to the register file. Okay, so data is also given. So for the write operation, we need to give RD and write data. Okay, this is the register file for archive instruction. So, but archive instruction use the storage register operand. The other instruction types use 1 and 2 register operands, right? So which means that if the register file supports archive instructions, then this register type can support other type of instructions, right? Because the archive instructions use the maximum number of register operands. Okay? And then actually we need to control the read write operation of register file, right? File. So think like the store instruction. Store instruction SW, actually SW, store word. Store instruction does not store the data in register file, right? The store instruction stores data to memory. So actually the store word, this instruction does not require register write operation. But this is just the electric signal. So which means that actually we can give any values to the this write register number and write data port. Okay. So for example, we can give 0 and 0 here. So actually the 0, it's okay because the 0 is always 0. So for example, 1 is given, but the data 0 is given to the write data port. So in this case, if we do not have the control signal, such as the leg write signal, then this data 0 is always written to the register file. Okay, even though this data is incorrect data. Okay, so we need to avoid this situation. So that's why register has the read write control signal, because some instructions does not require register write. Okay, so register write is controlled by read write control signal. Okay, so this is the register file. Okay. Okay. So Oh, 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 oh. Oh, oh. 그냥 T한테 좀 하겠습니다. Okay. So, so this is the RISC-V archive format instruction. Okay. So actually, so the instruction fetch step, the instruction is read from the instruction memory, and then in the using the this data field in the instruction, and we can give the required information to register file, right? So this is the example of archive instruction. So if we see that this instruction, you can find the RD field here, RS1 field is here, RS2 field is here. So what does that mean? So this instruction is the 32-bit data, okay? And then in this data, we can find the several fields like this. So actually, this RS1 field is given to the RS1. So read register 1 port of this register file, okay? And then RS2.
RS2.
RS2 is given to the read register 2 port of the register file. Okay. And then RD is also given to the write register port.
Right.
잠깐만요.
야, 맞네요.
Okay. So ID is given to the write to register port of the register file. Okay. Okay. So let's see the behavioral model of the register file. So I also mentioned that register file is similar to the memory, which means that that is the array of registers. Okay. So if we see that this behavioral model, like the memory, you can find the array format of the register file data. Okay. This means the size of a single register file is 31 down to 0. So it is because in the IV32I, the size of a single register file is 32 bit. And how many registers in this register file? 32, right? Because there are 32 integer registers in RISC-V. So it should be 0 to 31. So we can access register file like the RF data and then register number like this. Okay, so if we want access the register file number 1, so we can access like the RF number data 1. Okay, so and then register file needs to support 2 register reads and 1 register write. And then I mentioned that this register write is controlled by read write control signal. Okay, then how can we implement this behavior? So actually read operation is same to the memory. So when the data is read, then like this memory. So where is the memory? The memory. The corresponding data element is indexed by address. And then I mentioned that in the register file, we can use the register number as an index. So what is this one? Read data 1. So that is the read data for RS1. So this is RF underbar data and then indexed by register number. So it's a RS1. Okay, it's very simple, right? Now how about the write? So actually in this figure we cannot observe any clock signal, but we need to use the clock signal actually. Okay, in order to implement the register file in the single cycle processor. So this update is done at the rising edge of the clock, as you can see, and then it is enabled by read write. So what is this one? This is the actually D flip-flop with enable. Okay, because the write operation is enabled by read write signal. So which means that if read write signal becomes 1, then we can perform write operation. And how? So in this case, RF underbar data is updated by data input data, right? So we can find data input here. So RF data is updated by data in, but each element, this is indexed by RD, right? Because this is RD, okay? So RF data indexed by RD is updated by data in. So input data to register file if read write is 1. So and also you can find the, so this is the actually the register read or register write operation in RISC-V single cycle processor. And then also you can find the ALU is here. So this is the execution step, which means that if the, so in this example, you can find the add instruction is here. So it needs to perform add operation. So it requires two data from register file, and then add instruction is performed, and then result data is generated. So then ALU. So ALU is used for performing the required operation, like such as the add, sub, or exclusive, or some other logical instructions. So it's selected by ALU operation. So because ALU needs to support some different operations, these different operations are selected by ALU operation control signal. So based on this control signal, the ALU can perform add operation, sub operation, and then some other operations. Okay, but ALU requires the two input data, and then it generates the output result. Okay. So, and then actually we will learn about some detailed operation of ALU later. Okay. But you can just understand that ALU is just a combinational logic. So which means that two occurrence data are given to ALU, then ALU generates one result data after some delay. Okay, so let's think about the load and store instruction, like the load word x1 and immediate x2. Okay, so I can give it like now. So so let's see the example. Load word. Okay, load word x1 and immediate x2. So this is the example of load instruction. So load instruction is the actually I-type instruction. So what does that mean? So load instruction requires immediate data. Okay, and then using the base address in actually this is the RS1. Okay, using the base address in RS1, and then this RS1 is added with the immediate number, and then using we can calculate the target address. Okay, target address of this load word instruction, and then the data is read from the memory, and then this read data is written to register. So this is the RD. So for this load, also store instruction is the same, but this becomes the RS2, so another source register. So actually, in order to support the memory instruction, such as the load and store instruction, we need to perform RS1 plus immediate. So which means that we need to get immediate number from an instruction. And then this immediate number is to be added to the base address of in RS1. So this becomes the address. So this is the address. So this is the address. Okay. So for the load instruction, we need to read data from the data memory. So if the address is given, then in the data memory, we can get data, right? And then store instruction, then so we can generate the target address in the same way, which means that using the RS1 and then immediate number, so we can just calculate the target address of the store instruction using RS1 plus immediate. Okay, the address is given. So in the data memory, the address is given, then we can read the data. Okay, and then for the store instruction, we need to perform data store, okay, data write. So address is calculated like this, and the data is given. Okay, so this is the data memory. So actually, in order to calculate the address, we need to perform RS1 plus immediate, right? And actually, this operation is actually add operation. Okay, and add operation can be done by ALU, right? Because ALU needs to support the add instruction, which means that we can use ALU for computing target address of load word or store word. Okay, but what is the problem? If we see the ALU, then ALU needs to receive two operands, but this operand is the 32-bit data, 32-bit operands, right? And then it generates the 32-bit result. So it's actually we can use this value as the address because ALU can perform add operation. So and then RS1, the width of RS1 is the 32-bit, right? But immediate is the actually it's 12-bit. And it's a 2's complement. So what is required? ALU receives 32-bit data, but in order to calculate the address, but we immediate is the just 12-bit data. So actually, this data is to be extended to 32-bit. Okay. So you can find the immediate generator here. So this is the immediate generation unit, and actually the immediate generation unit generate the 32-bit data. Okay. So you can find all this is the 32-bit input to the immediate generator. So actually, it is because there are different kinds of immediate data format. So so I type, S and then S type, and B type or SV type. These instructions use different format of immediate field, right? So for example, so this is a different data. So actually for the I type data, so we just so actually this is the some behavior model of the immediate generation. So it means that we need to convert the 12-bit immediate number to the 32-bit number, 32-bit number data. So in order to perform the 12-bit to the 32-bit, and then I mentioned that this 12-bit is the 2's complement data, so which means it's a signed data. So which means we need to perform sign extension. Okay, and then this is the method for sign extension. So the I type data, so this is the I type field. So you can find that immediate number is stored in the upper 12-bit of an instruction, right? So in order to generate the 32-bit data, so the MSB is the sign bit. So MSB, so instead 31, MSB is repeated 20 times, and this immediate number is included. Okay? This is the sign extension. So MSB is just repeated again and again. So for the I-type instruction like the load word, we can generate the 32-bit number from the immediate field like this. How about the S-type? So this is the store word. So for the S-type instruction, the part of immediate number is stored in the upper 7-bit of instruction, and then lower part is stored in the this field. So also, so this MSB is the sign bit. So the inst31 is just repeated 20 times, and by combining the upper part and then lower part of the immediate number, we can generate the 32-bit number. Okay, so this is the S type. B type is so dirty, right? So you know the B type is so dirty, like here, but you know that the 32, 31 is the side bit. Okay, but in the B type, the LSB of the immediate number needs to be 0, right? So this is because actually immediate 12 down to 1 is stored in an instruction. So because the last bit is 0, okay? This is the B type, it's a branch type, like BQ. So for the branch instruction, so we need to generate the extended immediate number like this. Okay. So there are several different types of the immediate generation. So in order to simplify this operation, we just mentioned that the instruction is just given, and then we generate the 32-bit immediate number because the immediate number is included in the instruction. Okay? So that's why it's 32. But actually, we just generate the 32-bit immediate number from the 12-bit immediate field in an instruction. Okay, so the immediate number is extended to the 32-bit, and then this 32-bit data is given to the another port of the ALU. Then ALU performs add operation. You can generate the address for load word or store word. You understand? Okay, so address is given, and we can read the data. Or address is given, and then data is given, and then memory write operation is control signal is given, and the data is updated to the data memory. But data memory also has the memory read command, the control signal. Okay. So I already explained about the immediate format here, and then let's see the behavior model of data memory. Okay, so memory is same, so it's same to the instruction memory. So actually this should be D. So memory is a data array indexed by an address, and then as you can see, the size of a single array element is 32-bit in this case, because our RISC-V processor just supports load word and store word. Okay, this is the load word. Also, it accesses 32-bit data, the 4-byte data, and the store word also accesses 4-byte data. Okay, and as you can see, data has the 256 element. Then, how about the read operation? It's the same to the instruction memory, right? So read the data is if the mem read equal 1, then each data indexed by address, but the RISC-V address is a byte address, so address is need to be divided by 4. Okay, so it's indexed by data. Otherwise, if the mem read is 0, then 0 is read from the memory. Okay? So because the data memory has the mem read control signal. So if the mem read is 0, then data output becomes 0. Then how about the write operation? So it's also same to the, it's similar to the register files output and write operation, right? So if mem write is 1, it's an enable signal. Then, so this is data. The data is updated using data in. Okay, you can find the data in here. It's the right data. And then indexed by address. But it's address divided by 4 because the size is 32 bit. So this is the behavioral model of data memory. So you can find the clock here. So this is the design of data memory in a single cycle RISC-V processor. Then we need to support branch instruction. So this is the behavior of a branch instruction. The first, like the BQ, RS1, RS2, and target. Target is actually immediate number. Okay, it's immediate 12 down to 1. Okay. Okay, this is the behavior of branch instruction. So for performing branch instruction, then we need to read 2 source registers from register file. So it's okay. So RS1 is given to register file, alright, and then RS2 is given to register file also. Then we can get 2 register operand. Then we need to check the equality. How? A minus B equal 0, then it means A equal B, right? Okay, so now to check equality of 2 data, then we can perform some subtract operation. Okay, so ALU has the ALU also supports subtraction. So using the ALU, we can compare 2 source register operands. And then if the result is 0, then it means, oh, these 2 data are equal. Okay. So if you see the ALU, then you can find that ALU has the 0 port. Okay. Why? If the result is 0, and then if the ALU operation mode is subtraction, then 0 means that, oh, this means A is equal to B. Okay? Suppose this not to support branch instruction as BQ actually, then ALU has the 0 port. It becomes 1 if the output or ALU result becomes 0. Then ALU also needs the immediate. Okay. Then what is the behavior of ALU? If the ALU condition is true, I don't know. What is the behavior of BQ? If the BQ condition is true, which means that RS1 is equal to RS2, then PC is updated by current PC plus immediate. Okay. So we need to support this operation also. So immediate. So actually, I showed is immediate field of the P type, the branch instruction. So we can generate the immediate number like this. And then we need to perform add operation. How? ALU. We cannot use ALU. Why? Because we already use ALU for this operation, A minus B. Okay? So in this case, we cannot use ALU. So which means that we need additional adder to calculate the target PC of the branch instruction at the current PC plus immediate. Okay, and then this value is updated to the program counter. So let's see how. So when the BQ is executed, BQ, then RS1 is given to the read register 1 port of the register file, and RS2 is given. Then we can get RS1 data from read data 1 port, and then RS2 data from the read data 2 port of the register file. And then for the branch instruction like BQ, then ALU performs subtraction. Then we can get 0 if the RS1 data is equal to RS2. Then how can we calculate the target of the branch? So we can get immediate number from the instruction, okay? And then this immediate number is added to this is the PC curve, the current PC, added to the PC on the curve. So shift left 1 means that it's this operation. Okay? Actually, it represents the one bit of 0 is inserted at the RISC-V of the immediate number. So using this adder, then we can get PC curve, current PC plus immediate 12 down to 1. Okay, so immediate need to be extended, sign extended to 32 bit. Okay, and then this becomes the target of the branch instruction. So for the branch instruction, we require additional adder because we use ALU for comparison. Okay. So actually, so this is the R-time instruction, and then so for the branch instruction path, you can find this new. Okay. So you can find additional paths like here. Okay. So actually, we already learned PC plus 4. So this is the, so it is the PC curve, the current PC, CURR, and then, you know, this is the PC curve plus 4. Then what is this value? So this value is the, you know, the another input is, this is the PC curve, right? PC underbar curve, the current PC, and then, you know, the immediate number is added to the PC underbar curve, so which is PC underbar curve plus immediate. So this is the target of the branch instruction. So for the branch instruction, and the branch instruction is executed. So based on the result of a branch instruction, so I said that this is the PC underbar next. So that is the program count of next instruction. So based on the result of a branch instruction, PC underbar next can be PC underbar curve plus 4. This is the normal next instruction, or the PC next can be the target of branch instruction. That is PC underbar curve plus immediate. Okay, so we need to select, right? We need to select from these two cases, and then so one of these cases need to be PC underbar next. So for this selection, we require multiplexer, and then this multiplexer is controlled by PC source. It's a control signal. So based on this PC source, then the PC next can be PC underbar curl plus 4 normal next instruction, or PC underbar curl plus immediate, that is the target of a branch instruction. Okay, so this is the PC source. You can observe another multiplexer here. Why? For the R-type instruction, for like the add x1, x2, x3. So R-type instruction requires two register operands, right? So one is came from read data 1, and then the second one came from read data 2. But sometimes we use load word. This is the I-type instruction, and then we need to perform RS1 plus immediate. Okay, so sometimes we require RS1 plus RS2, or sometimes we need to perform RS1 plus immediate. So which means the second input of ALU can be RS2 data or immediate number. So there have to be two possible cases. So in this case, we need to add multiplexer, and then this multiplexer is controlled by ALU source. Okay, you understand? Also, we can find another multiplexer here. Why? So, and then if you see that this multiplexer, so you can find that one of the input of this multiplexer is from memory, data memory, and then another input comes from ALU region. Why? Add x1 or load word x1. So if we just perform add instruction, R-type instruction, then the target, the destination register is updated by result from ALU. Okay, and then if we just perform load instruction, the load word, then the destination register is updated by data from data memory. So there are two different cases. So in this case, there are two possible cases, then we need to use multiplexer. So this multiplexer is controlled by this selection signal. It is because we can update the destination register using the ALU result or the data from data memory. Okay, so this is the full data path of single cycle RISC-V processing. Okay. This single cycle RISC-V processor implements the all required steps for executing instructions. Okay, as I explained. Okay, so I hope you can understand how to build the data path of the single cycle RISC-V processor. Okay, any question? Thank you for your attention. Sorry for the unexpected mic issue. 감사합니다.